Good morning. I'd like to talk about stability today. It often happens when you're solving an initial value problem of the type that we're interested in, that the solution is the sum of two terms, one of which I'll call y1, the other y2, with the y2 tending to 0 as t increases. We'll call the y2 the transient part of the solution. It almost goes without saying that a numerical method, if it's any good, should reproduce that behavior. If your solution consists of two terms, one of which tends to 0, then applying the numerical method to that problem should tend to 0 as t increases. People have developed a standard test program for this. The standard test problem is derivative of y with respect to t equals negative lambda times y, where lambda is a positive constant. Y at the beginning of the interval of t numbers is taken to be some number alpha, which is not 0. The exact solution of this test problem is easy to find. Rewrite the equation as 1 over y times the derivative of y equals negative lambda, and then integrate both sides with respect to t. You find out that the natural log of y needs to be negative lambda t plus a constant, meaning that y itself has to be e raised to the power negative lambda t plus a constant. Using properties of exponentials, of course, you can write the e to the c factor out front, and I'll call that number a. Y needs to be a e to the minus lambda t. Also, if we assume that we start at t equals 0, then the a turns out to be the initial value of y at t0, which we have also called alpha. This function, a constant times exponential of a positive number times t, certainly tends to 0, literally exponentially. We're going to say that a numerical method is stable if this happens. When you take whatever method that you have in question and apply it to a test problem of this nature, if you are guaranteed that as t increases, the computed solution tends to 0, that's what we're going to call a stable method. The simplest numerical method that we have is Euler's method. So let's apply this stability criterion to Euler's method. The differential equation that we'll use then is derivative of y with respect to t equals negative lambda times y. That means the f of t and y is just negative lambda times y. Euler's method says the estimate at time I plus 1 is the estimate at time I plus delta t times the right-hand side of the differential equation evaluated at TIWI. For our test problem, the right-hand side of the differential equation is going to be negative lambda times the y value, which, applying to Euler's method, says that wi plus 1 is wi plus delta t multiplied by negative lambda times wi, which you can easily rearrange into this format. This is Euler's method applied to our standard test problem. How does this behave mathematically? Although it may seem obvious, we will go through the details. If you let I equal 0, then I plus 1 will be 1. W1 is 1 minus lambda delta t times W0. W2 is 1 minus lambda delta t times W1, but we've just figured out what W1 was. So simplifying, W2 is 1 minus lambda delta t quantity squared times the initial value of y. W3 is 1 minus lambda delta t times W2, which we just figured out. So after simplifying, W3 is 1 minus lambda delta t raised to the third power times the initial value of y. If the absolute value of 1 minus lambda delta t is less than 1, then powers of 1 minus lambda delta t will tend to 0 as the power increases. Therefore, the wj's will tend to 0 as j increases. On the other hand, if that absolute value is larger than 1, that says that the wj's are getting steadily larger in absolute value, and the wj's will not tend to 0 as j increases. We say that Euler is conditionally stable because there is a condition, namely this, for which Euler's method will be stable. The computed solution of our test problem will tend to 0. However, if that condition isn't true, then we don't get a computed solution that tends to 0. Let's look at what that condition means. If the absolute value of a quantity is less than 1, then that means that the quantity itself must be between 1 and negative 1. So we have a double inequality to solve here. If you subtract 1 from all three members of this inequality, you find out that it becomes negative 2 is less than negative lambda times delta t, which needs to be less than 0. Now, this part, the negative lambda t less than 0, is always true. In our test problem, lambda is positive, delta t is positive, lambda delta t is positive, so negative lambda delta t is automatically negative. So this part of the inequality is not important to me. Not important in the sense that it doesn't place any kind of condition on when I get stability. The other part, though, is more interesting. Negative 2 is less than negative lambda times delta t. If you multiply both sides of that inequality by negative 1, the inequality sign flips over, and we find out that 2 needs to be larger than lambda times delta t. That means lambda delta t needs to be less than 2, or in a more applied way of thinking, the time step delta t has to be smaller than 2 over lambda. So we have a claim now. In our sample problem, if delta t is less than 2 over lambda, the computed solution of the sample problem will tend to 0 as it's supposed to, and otherwise it won't. So summarizing what we've figured out, Euler is stable if delta t is small enough, but not stable otherwise. We say that Euler is conditionally stable. What about a similar analysis if we want to look at the backwards Euler method? You'll remember that that's a one-step method, except the step that we use is in the future. Wi plus 1 is Wi plus delta t times an f value, but we don't evaluate at the current time value in the current approximation to the solution. We evaluate it at the next time step and the approximation to y that goes with that time step. Let's apply backward Euler to our sample problem. The right-hand side function is the same as it was before, so wi plus 1 is going to be wi minus lambda times delta t times the approximation to the y value at time ti plus 1. So this is a different formula than what we got with Euler's method. It's not very complicated, though. We're supposed to already know wi. We know lambda from the differential equation. We know delta t, that's our time step. It's b minus a over the number of steps. The only thing we don't know in this equation is wi plus 1. And the way that wi plus 1 appears in this equation is particularly simple. Add this term to both sides and factor out the wi plus 1. Divide through by the number 1 plus lambda delta t, and this is how you would do backward Euler's method in exact arithmetic on our test problem. Not to insult your intelligence, but carrying out the same sort of calculations that we did before, W1 is 1 over 1 plus lambda delta t W0. W2 is 1 over 1 plus lambda delta t times W1, which we just figured out. So you end up with 1 over the square of 1 plus lambda delta t times W0. W3 is pretty much what you would expect it to be. We have a pattern here that's basically the same sort of pattern as we had for regular Euler. So the approximation given by backwards Euler for time step j is going to be 1 over the j power of 1 plus lambda delta t, all multiplied by W0. But things are great now. Lambda and delta t are positive. That means 1 plus lambda delta t is bigger than 1, which means the reciprocal of that, being a positive number, 1 plus lambda delta t has a reciprocal that's positive, but on the other hand, the positive number on the bottom is bigger than the positive number on top. So 1 over 1 plus lambda delta t is at least 0 and is less than 1. That means the powers of these quantities tend to 0. Wj then will be a quantity that's tending to 0 times a constant. In contrast to what happened with Euler, where you got stability only for certain delta t's, backwards Euler is stable regardless of what t is. Sometimes people call this unconditionally stable. I want to make a comment here. I'm not necessarily talking about how accurate the methods are. I'm talking about a qualitative behavior. We have this test problem. In the exact solution, the test problem tends to 0 as t increases. What we're concerning ourselves with, does the numerically computed version of the test problem act that way? What we figured out is, for Euler, if delta t is small enough, the answer will be yes, and if it's not small enough, the answer will be no. Also, the answer to that question for backwards Euler is yes, period. We're about done talking about the theory ideas. I want to actually try this out on a computer program. So I'm going to pick the lambda to be 10. dy dt is negative lambda times y. negative 10 times y. Y evaluated at t equals 0 is going to be 1. It's not very hard to verify that the exact solution is y equals e raised to the negative 10t power, which obviously approaches 0 very rapidly as t increases. We're going to solve this on the interval from 0 to 23. To make sure that our thinking is right, let's figure out when Euler is going to be stable for this particular test problem. I'm going to have lambda equal 10. We're doing the interval from t equals 0 to 23. To get stability, delta t needs to be less than 2 over lambda, that is 2 over 10, which is 1/5. On the other hand, delta t is the width of the interval, 23, divided by the number of steps we're going to do. So to get stability, it needs to be true that 23 over n is less than 1/5. N's positive, so you can multiply both sides of the inequality by n without altering the inequality sign. The same is true for 5. So it turns out that 115 needs to be less than n. N needs to be bigger than 115. So we have a prediction here. If n is bigger than 115, the sample problem using Euler's method will be stable. The computed solution will approach 0. If n is not bigger than 115, that won't happen. So we've got a very concrete prediction here now. I've written new versions of the Euler code and also others. Let's have a look at my Euler code. So the rewrite is extremely minor. Initially, I'm going to set n steps equal to 200. We have all the usual declarations. This time a is 0 because that's my starting t value. B is 23. I initialize the first of my y approximations to be 1. Other than that, everything is as usual. So we're just doing the usual Euler method here. The code that calculates the actual solution is going to return e raised to the negative 10t power, because that's the exact solution of my problem. And the right-hand side of our differential equation is now going to be negative 10 times the current y value. So this is just to show we are working on the problem that we said we were going to. So I'm going to compile this. I've set n steps equal to 200. And we said that as long as the number of steps was bigger than 115, the qualitative behavior of the computed solution will be right. But I'm not interested really in how accurate it is. I'm interested in the qualitative behavior. So I'm actually going to look at the numbers in the Euler file, and I just want a yes or no question. Are they getting small as t gets bigger? And the answer, obviously, is yes. By the time I'm down to the middle of this first page, the computed solution is roughly 10 to the negative 10 in magnitude. And as you continue, it becomes very small. The numbers towards the end are of magnitude 10 to the negative 165. So certainly the behavior that we were expecting out of Euler with n steps equal to 200 is what we actually get. Let's change that. Let's go back up to the top. And I'm going to change the number of steps from 200 to 150. 150 is still bigger than 115, so it should still qualitatively act correctly. And as you can see, by the middle of the first page, the computed solution is of size about 10 to the minus 4. And as you proceed, it becomes smaller. Notice it isn't getting small quite as fast as it did before, but it is getting smaller. Let's get dangerously close to the cutoff, though. 120. Now you see, by the middle of the first screen, the computed solution is about negative 0.322, which is not nearly as small as it was before. But on the other hand, if you look at these numbers, they're getting steadily smaller in absolute value. So the qualitative behavior is correct, but we're not seeing it as dramatically as we saw at the beginning. It doesn't take a rocket scientist to guess what's going to happen here. The closer we get to that magic cutoff number, the less nice things are going to be. 116 is just barely on the good side of the limit. So you see 1, negative 0.98, positive 0.96, negative 0.94. The computed solution is decreasing in magnitude, absolutely true, but it's taking a good while to do it. By the time I get down to the end, it's only down to 0.13299. What if we do exactly n steps equals 115? The prediction is that we are not going to see this nice 10 to 0 type behavior. On the other hand, we're right on the edge, so it'll be interesting to see what happens here. The computed solution bounces back and forth between values -1 and +1. The computed solution does not approach 0, so strictly speaking, we would have to say we don't have stability. On the other hand, the solution doesn't run out of control or anything either. It's just that it doesn't tend to 0. And lastly, for Euler, 100 is below the cutoff here, the line between the good behavior and the bad behavior. Solutions: 1, negative 1.3, positive 1.69. By the end of the first screen, the magnitude of the solution is 321. Then it gets worse. Then it gets worse after that. Then it gets worse after that. And by the time we get down to the end, the computed solution, which is supposed to be getting close to zero, is gigantic. This is the instability of the method showing. I said that was the last one. But I can't resist seeing what happens when the number of steps is 50. As you can see, the computed solution seems to be getting bigger in magnitude by a factor of roughly 3 or 4 every step. This is very disturbing if we think life always has to be easy. I started at t equals 0, doing one step of this method. The computed solution is negative 3.6, whereas it's supposed to be decreasing and getting close to 0. Looking at a few more pages, it's getting gigantic. By the end of the calculation, the computed solution is about 6 times 10 to the 27th power. So there's no doubt about it. Our analysis of the Euler method is right. Let's try a Runge Kutta of order 4. Initially, we'll start off with 200 steps. Everything else is exactly as it was for the Euler problem. We've not done the same kind of analysis that we did before for the Euler method. So we don't know exactly where, if any place, there's going to be a change in behavior. It's conceivable that Runge Kutta 4, being such an accurate method, will never have stability problems. On the other hand, it's equally possible that somewhere, if you make the number of steps too small, you're going to get into exactly the same kind of issues that you did with the Euler method. So we're just going to do some experiments here to finish up. So I'm going to compile my code. This is with the number of steps equal 200. I'm not going to look at Euler now. I'm going to look at the solution for RK4 as computed. And as you can see, everything's fine. Middle of the screen, you're about 10 to the minus 7. And by the end, the computed solution is tiny. It's roughly 7 times 10 to the 97th power. So everything is good. At first, let's try changing the number of steps. As I said, we haven't done the similar kind of analysis for this, so I don't really know exactly where, if any place, we're going to start seeing trouble. So I'll try 150. I'm just experimenting. For 150 as a value for n steps, there's no problem. How about 125? Still, no problem. Maybe it's possible that this RK4 method is good no matter what the number of steps is. Let's try 100. Everything is still good. It seems like we're just wasting our time. Let's try 50. And then suddenly we see a big problem. Runge Kutta 4, which many people regard as the only numerical solver you'll ever need, fails badly on a very simple test problem. The computed solution using Runge Kutta 4 is not getting small. Towards the end, it's about 4 times 10 to the 48th power. This turns out to be typical. Explicit methods tend to have stability problems. Implicit methods tend to have less stability problems. So one of the reasons that we study all of these different kind of methods is, while a method may work well on one particular problem, it's just as likely that you can have another problem for which it fails badly. And this is an example of this. If anyone ever tells you something like, well, you only need Runge Kutta, that'll do everything you want, either they're joking with you or their knowledge of the subject is less than you might wish it to be. In any case, I hope everyone's having a good day. I'll talk to you again soon.